Thanks a lot to the organizers for the for putting together this workshop and also for the opportunity to give the talk here and for the invitation. Okay, it's really a pleasure to be back at UCLA to talk about tensor networks. Okay, so this morning we already had a couple of talks, okay, on tensor networks regarding different topics, and my talk is going to be more related to the second one by Benjamin, because I come from physics, so I'm going to be talking to you about tensor networks from a physical point of view. And in particular, what I wanted to tell you today is about some recent developments that we have been working on the simulation of quantum computers with tensor networks. Okay, somehow similar to what we saw this morning, but you will see that it's a little bit different. And also on some recent developments also on applying tensor networks to improve machine learning algorithms. Now, that is a very generic story to apply tensor networks to improve machine learning. So I wanted to focus it for this talk, for the sake of this talk, a little bit more on large language models, okay? ChatGPT and all this sort of stuff. I could be talking here a lot about machine learning, but I prefer to specifically explain you about the developments that we have been doing for large language models, which in my opinion are very relevant. Okay, so that's exactly the menu that we have for today. Actually, I want to start talking about quantum computing, okay? So I reversed the order with respect to the title. When talking about simulation of quantum computers, what I'm going to be explaining you is about the tensor network simulation of the IBM quantum computer. Okay, IBM proposed an experiment on their quantum computer on the simulation. It was a quantum simulation of the dynamics of a kick-Tising model, okay? And there was a lot of noise about that. And I will tell you exactly about how it's actually possible to simulate that very efficiently with tensor networks, not just the model, not just the system that IBM wanted to simulate, but also much larger systems, okay? That's the first thing that I want to explain you today. Second thing is about the compression of large language models. Large language models such as ChatGPT and so on that you have been probably using, they are very cool, but as I will explain you later, they have a fundamental problem, which is that the memory that they're using is huge, okay? They are just consuming so much energy that it's impossible to actually scale up those algorithms, and also they are just, consuming so much energy that it's impossible to develop them further. One needs to come up with ideas to compress these methods, okay? And otherwise AI is gonna be burning the planet very soon, and that's exactly what we are proposing to do with tensor networks. So that's what I want to explain you today. Okay, well, let's start by talking a little bit about tensor networks. This is a tensor network workshop. So this is a very generic introduction, but I was told to actually make the talk accessible to everybody, okay? So I'm gonna explain you tensor networks a little bit from scratch. And this is an introduction, let's say, from a physics point of view, okay? Now, what we realize in physics is that the Hilbert space of a quantum many-body system is huge. Is what, in the words of Frank Verstraete, who is not here today, is a convenient illusion. Now, the Hilbert space of a quantum many-body system is nothing but the vector space where the states that physically represent something for a quantum system are actually living in, okay? This is a vector space, okay, with exponentially many vectors inside, right? If I have, let's say, n spins, the size of this Hilbert space is going to be of the order of 2 to the n, okay? That's the dimension, okay, of the Hilbert space, and therefore the total number of vectors that I have in this vector space is huge, okay? This is really very, very large. Now, in physics, we say that this is a convenient illusion because if you have a look at the state that nature is actually realizing, it turns out that most of the time you are not in just this huge place, okay? You are in a very concrete corner of this Hilbert space, okay? The corner of the relevant states of nature, okay, is actually very, very small compared to the overall space. It's actually exponentially small. Okay, this is a little bit of a representation of what is going on. This space has sort of an onion-like structure. You can think of the set of product states. This is what in physics we call mean field. This will correspond to those states that are not a superposition of any states in a given base, in any local basis. Okay. Now it turns out that the states in nature that correspond to low energies for local Hamiltonians means those systems for which interactions are local, okay? People are, the spins or your atoms are talking between nearest neighbors, but they are not completely delocalized in terms of interactions. Turns out that the low energy eigenstates of those systems, they are not product states, but almost, okay? Is this possible to prove? and also the states that satisfy something that in quantum information theory we call the area law of the entanglement entropy. It's also like a very small corner of the Hilbert space.
Do you know the dimensions of this?
Huh?
Do you know the dimensions of the area law states?
It's possible, yeah. Well, actually, I don't remember them, but it's people have quantified this. Okay.
I'm not sure they have an actual dimension. No?
In the paper by Jens, it's a pity that Jens didn't come, actually, but I think they did some numerical estimation. Right.
But, for example, is there some bound polynomial in there?
Yes, there are bounds. Okay, so this is, I mean, what is possible to prove is that when you increase the number of atoms that you have in your system, the size of the overall Hilbert space is actually growing much faster than the size of this corner.
I understand, but there's a big difference between 2 to the n and n to the 100 or n squared or or you don't know.
Yeah, no, I don't remember exactly what is the actual, the quantity.
Well,
I mean, I know the
well, you can count parameters, right?
Exactly.
Upper bounds. So if you have a square lattice tensor network of one dimension d with n sides, then you have d to the 4 times n parameters, right?
Polynomial.
So it's linear in n,
right, but
linear in n, yes.
Always a one dimension.
But what are we taking for g? That's like
no, exactly.
Well,
No, but
this
is a constant. Yeah, it is a constant in this approach.
Play different games. No, you could say d goes polynomially with n, then you get the d and to the fifth and so on.
Yes, so that's my question. Are people taking d constant?
Yes.
Okay.
Yep.
So that, I know the answer to the first two,
Okay.
and now just the third.
Well, that's worse.
Yeah, this is worse. This is worse because there is no bond. There is no tensor network here. It's just the area law that is satisfied. This is another property. Okay. But I think in the paper there are some bounds, but I don't remember them exactly.
I mean, personally, I think the area law is highly overrated.
Yeah.
So I wouldn't worry too much. That's my opinion.
Okay.
So the bottom two, if we take d constant, I'm very happy. I know what these things are.
Nice thing also here is that if you do this counting of parameters and you start adding more atoms into your system, the size of the overall Hilbert space is growing exponentially fast, whereas the size of these corners here is growing polynomially. Yeah. It means that as your system gets larger and larger, these corners are more and more irrelevant. Okay, and this is exactly what happens, because in real life, when you have what we call in physics a many-body system, you typically have of the order of 10 to the 23 atoms, okay? This is the Avogadro number, and this is a number that in physics and chemistry we consider when you have a macroscopic piece of material, okay? You have more or less of the order of 10 to 23 entities, okay? Atoms, electrons, or something. Now, if you go to 10 to the 23, this is a super exponentially large, and you realize that this corner is almost irrelevant, okay? But it turns out that nature is living there. Okay, nature is living there at low energies. It's even worse than that because people also proved that if you try to access the rest of the Hilbert space by time evolution, by dynamical evolution, with some Hamiltonian that is also local, turns out that it takes an exponential amount of time. Okay, it's really a very bad situation.
Sorry, Sorry, is this like a theorem?
Yes.
And
this is a theorem. Yeah. Yeah, it was actually proven. It's a very nice paper, actually, from 2011, from David Poulin, from Verstraete, Rolando Soma, and Angie Quarry. Yeah. And the constraint here is that the Hamiltonian that generates the time evolution, okay, which is it's local. Yeah, it's local.
And that's considered real.
Exactly. So essentially, it's telling you that if you start in a state that is in this corner here, and you try to get out of it just by doing time evolution with a local Hamiltonian, you don't go much farther than this corner here. Okay, exploring all this space requires either non-local interactions or something else.
Of course, in the end, you somehow care about closure properties, right? You don't care if you get all states. I think the basic argument is parameter counting, right?
Yeah.
Of course, really cares can you get epsilon close to any state. And, I'm not sure what this paper says.
That paper is also parameter counting, yeah.
Yeah. Because that's not really what you want. No, I
Exactly.
don't care if I get a state exact.
Exactly.
If I can get epsilon close, I'm good.
Okay. Good. Well, it's telling you that if you want to explore this space, if you have a system that is, let's say, macroscopic, it's going to take off the order of 10 to the 23 seconds, and that's exponentially larger than the age of the universe, which, according to astronomers, is of the order of 10 to the 17 seconds. So, it means that somebody is making a big mistake here, okay? It means that we need that, if we want to characterize quantum many-body systems, we need a language not to target the full Hilbert space, but actually this corner, all right? And that language is exactly tensor networks. This is why we discovered tensor networks in quantum many-body physics, okay? This is the natural structure of low-energy states of matter, okay? That's what it is. Now, well, yeah.
I just have one more question on that slide. Right. On the left, we have a function of n, and on the right, there's no n.
Yeah, I've
10 to the 10 to the 23rd.
N is 10 to the 23.
N is 10 to the 23.
In the right example, yes.
And but that's
very
that's a big number.
Yeah, well, yeah. This has of the order of 10 to the 23 atoms, okay? The pointer. That's, okay? Pick up any piece of superconducting material. Okay. It's a big number, yeah. It's a big number, but those are the systems we consider.
Okay.
Okay? It's not 10 atoms or 1,000, it's 10 to the 23. Okay, we want to study phases of matter and so on. That's exactly the number that we are interested in. Okay, that's what in physics we call the thermodynamic limit. It's the limit where you have infinitely many atoms, okay, and everything is translation invariant, and there you see the emerging properties of macroscopic matter emerging, okay? That's where you see it. Okay, well, what are tensor networks? Tensor networks are in this context, okay, are nothing but picking up the coefficient of the quantum many-body wave function in a given basis. This is nothing but a vector in a high-dimensional vector space, all right? And consider it as a multidimensional tensor, and for me a tensor is nothing but an array of complex numbers, okay? Now a tensor network is a decomposition of this big monster in terms of something that is more efficient, namely a tensor network, which is nothing but, as you know, it's a network of interconnected tensors according to some network pattern. Now, examples of tensor networks, a matrix protostate, okay, which is nothing but a 1D array of tensors or a tensor train, all right? There are many numerical techniques that are based on MPS, DMRG, we have Steve here, but also power wave function renormalization group, TEVD for computing dynamics, and even more. And there are different types of indices in a tensor network in physics. We call them physical indices or bond indices. Okay, the physical indices are the ones corresponding to the original vector spaces, the ones that define my Hilbert space, and the bond indices are the ones that are connecting the tensors among each other, all right? And the size of these indices is called the bond dimension. We call it D. I think in the previous call it was called chi. Depending on the paper that you look at, they call it D or M or chi or or R, okay, and so on. Okay, we can be more creative and go to higher dimensional structures. For instance, in 2D or 3D, there is something called projected entangled pair states, okay? Or tensor product states, depending on where you look at. This is nothing but a higher dimensional generalization of MPS. And there are also, many numerical approaches for simulating systems with this type of structure, okay? And here you can be as creative as you want, depending on the structure of correlations in your quantum state. The tensor network that is going to describe your system is going to be one or another. No, this is another example that is called the multi-scale entanglement renormalization ansatz, or MERA. This actually showed up also very briefly in the previous talk. But this structure is actually very nice because it has an extra dimension that corresponds to something that in physics we call a renormalization group flow. Okay, I will not enter into that. Just to mention also that this turns out to find also many applications in quantum gravity, string theory, and all this. Okay. Now, why is all this very nice? Well, because when making this decomposition, actually we find something that is efficient in the number of atoms that they have. Okay. The number of parameters in all these structures, as you know, it's scaling polynomially with the number of atoms. Okay, polynomially named. It's satisfying that property that I was saying before, that in physics we call the Area law, and it also corresponds to low energy eigenstates of local Hamiltonians. For all these, there are actual theorems proving that.
So the matrix product states and the projected entangled pair states, this makes sense from a geometric point of view if you're envisioning, atoms along a line or in a two-dimensional array. Is there some geometric thing going on over there? Yes.
This is actually the correlations have an emerging dimension. Okay. In these systems, actually, what is happening is that the correlations in the quantum system, they are spread, let's say, or they organize themselves along the physical dimensions where they are living. Okay. Now, there are we know for examples in physics where this actually does not happen. Okay, an example is what we call the quantum critical point of a 1D system. This is when you have a phase transition. Let's say when you go from water boiling to water being vapor. Okay, that's a phase transition exactly at the point in the middle. Now, for quantum systems at zero temperature, there is also something like this. Okay, let's call a quantum phase transition. And when you are at a quantum critical point, let's say from a ferromagnet to a paramagnet or something like this, correlations and entanglement and all these things diverge. Okay, they have a very specific structure, and they actually correspond to that. Okay, there is an extra holographic dimension that is emerging in the system.
Maybe I don't know who, but sometime this week it'd be nice to have a talk just explaining that.
Okay.
Explaining what?
The meta.
Critical points or meta?
Or critical points.
Why that graph has to do with something physical?
We could do that, yeah. Okay, more questions? Or other wishes? Is somebody writing the wish list for this week? No? But that's a good point, yeah.
You know, as a mathematician,
there is a whole story behind this, yeah. Okay. Good. Okay, so you know, always when I talk about tensor networks, I like to put this slide because at the beginning, you know, something that I noticed is that every 10 years on average, somebody rediscovers tensor networks in a different field. Okay, that's exactly what happens. You know, that we found them in physics, we found it in mathematics, and now people are finding also in machine learning. But over the years, we have been finding applications of tensor network states in a variety of scenarios, okay? Not just in the simulation of strongly correlated systems, classical statistical mechanics, and mathematics as well. But also, as I was saying now, that also in machine learning, in quantum chemistry, nuclear physics, to benchmark quantum computers, in high energy physics, also to simulate, you know, what the people call lattice gauge theories, which are the models, okay, of high energy physics, of how particles actually are interacting at high energies, okay, in particle accelerators, and also even in string theory and quantum gravity, there are very nice connections of how the structure of a space-time itself is connecting to tensor networks. Okay, that's something that actually is really very, very nice. Now, when you want to simulate a system, or when you want to improve a machine learning algorithm, now you have to choose your favorite tensor network, and you come to the point in which you have to make a commitment, okay? Which is my fighter, okay? Turns out that depending on the tensor network that you choose, you are going to find some properties or another, or you are going to have some algorithms, or you are going to have another algorithm, and the results are going to be very different, okay? Here are some examples of tensor networks that people have been proposing over the years. Obviously, matrix Prote states, option A, or tensor trains, no? But also the 2D generalizations, what I was calling before PEPs, 3 tensor networks also. I think they were also mentioned briefly this morning in Benjamin's talk, no? These are also very nice. The multi-scale entanglement renormalization ansatz. And you know, you can get more and more complicated here. The limit is your creativity. For instance, this one here is called the branching meta, okay? That also corresponds to another type of structure of correlations. And you can also represent operators, okay? If you have what we call matrix product operators, or MPO, PEPs operators, matrix product density operators, and so on and so forth. So depending on the structure of the correlations of your system, you may choose one or another. And also depending on what are your computational capabilities, you may choose one or another, okay? Good. Okay, questions so far? No? All right, so let's move on. And now I want to explain you about simulating the quantum computer from IBM, okay? Not the one by Google, okay? You can be, that's okay. The one by IBM. Now, what we are simulating is actually an experiment that IBM proposed. Well, there was this paper from IBM in June 2023, I think. It was in the cover of Nature, okay? And there was also a lot of noise regarding that simulation. They were also in videos and interviews and so on. There was a lot of noise, okay? And why was that? Well, it was because, you know, IBM essentially published this paper in Nature, okay, where they did the simulation of, you know, exactly, they did a quantum simulation, okay, of a quantum many-body system that, according to them, could not be simulated via classical computation, okay? Or at least it was not so obvious how to do that. Now, the nice thing about this paper is that they did error mitigation techniques that were quite unprecedented for 127 qubits. This is the Eagle quantum processor, okay? They call it Eagle for 127 qubits. It's actually a processor that, as far as I know, they have it very well under control. They know very well how to suppress the error, and they have these error mitigation techniques that allow them to predict how will be the result of the measurements if there were no error, okay? That's actually something very cool, and in this paper, they introduced some new ideas that were actually very, very powerful. This is the processor. Well, actually, the processor is inside of this cage, no? This is the Eagle 127 qubit quantum processor. It looks like Batman's quantum computer, okay? Super black. This is actually the topology of interactions of the 127 qubits. This is the actual process. This is how the actual processor looks like, okay? And in the nodes of this lattice, you have the qubits. Now, this lattice is what in condensed matter physics we call a heavy hexagon lattice. Okay, it's like a honeycomb lattice, but with some extra nodes. Now, what did they do? They actually simulated the dynamics of a quantumizing model with a transverse field for a spin 1/2. Now, this is kind of the simplest quantum model that we can think of in quantum many-body physics. Okay, it's a it's a Hamiltonian that has two types of terms. Okay, the first term is spin-spin interactions. Here are qubit-qubit interactions. Okay. Among nearest neighbors, so we have qubits or spins on all the nodes of the heavy hexagon lattice, and there are nearest neighbor couplings, okay? And each qubit is interacting with the neighbors according to a ZZ coupling, okay? These are Pauli Z matrices. And now there is also another term that we call a uniform magnetic field, and this is actually, a sum over all the possible qubits, okay, of the Pauli matrix X.
Some of these qubits look like they're attached to 3.
Yes.
So there's no triple interactions.
Well, in the case of, so there are some qubits that have 2 neighbors and some other qubits that have 3 neighbors. Yeah. That's correct. So for the ones that have 2 neighbors, you have interactions with the 2 neighbors, and for the ones that have 3 neighbors, you have interactions with the 3 neighbors. Yeah.
But the key thing is they match the lattice to the geometry of the qubits.
They match the lattice to the geometry of the qubits. That's exactly what they did. Yeah, to make it easy, let's say. Yeah. So for every link on the lattice, sorry, for every link on the quantum processor, okay. So for every coupling that they have between different qubits, they actually have an interacting terms in the Hamiltonian. They match the problem to the actual topology of the quantum processor.
So every edge gets a ZIZ.
Exactly.
That's
it. Yeah. And then every node gets an X. Okay? Good. So how do we do the quantum simulation of the dynamics of this? Actually, it's possible to split this Hamiltonian into 3 pieces. The interactions that correspond to the green links, to the red links, and to the blue links. Now, if you realize, for instance, for the red links, all the terms in the red links, they don't touch with each other because they correspond to qubits that don't overlap with themselves. So it means that all these terms commute with each other. Okay. The same story for the red.
It's one Z interactions.
Well, obviously, you are right. Okay, but they don't have but there are no overlapping qubits. Okay.
What's the Z? Can you remind us?
No, exactly. What I'm saying is that all these interactions.
What is ZI? What is that operator?
Oh, this is the Pauli matrix. Okay. 1 minus 1 0 0.
And X?
Okay. X is the X Pauli matrix 0 1 1 0. Yeah. Okay. Good. So this is actually what they did. The quantum circuit that they simulated looks like that. They have first, a row of 1 qubit gates, and then they have like 3 layers of 2 qubit gates. The red layer is acting on the red links, the blue layer is acting on the blue links, and the green layer is acting on the green links. Okay, and then repeating this over many, many steps, they are just simulating a time evolution with the system. These are some of the results that they obtained for some expectation values of magnetization. That is the expectation value of Z, okay, and some other expectation values, okay, that are actually non-local and so on. You can see here some plots. Now the nice thing is that they had some approximation of the exact solution of the time evolution, okay, and they saw that with the error mitigation techniques, actually they match pretty well and with low error the actual exact solution, whereas with simulations with, let's say, tensor networks that perhaps were the appropriate ones, they were actually not finding the correct solution, and they were getting a lot of error, okay? And they were motivated then to say that the quantum computer is providing results where tensor methods break down, and we have now reached reliability, blah, blah, blah. Okay. Well, this is nice from the point of view of the quantum simulation is fantastic, okay? So they are really matching the correct result. The problem is that these tensor network results here, they were not accurate because they were not using the right tensor network to simulate the system. If you have this system, and this is a 2D system, what they were actually using to simulate the system was more of a 1D snake or something like this, whereas the natural thing to use here is actually a 2D tensor network, okay? Well, that's actually what we did. What if we use other two-dimensional tensor network algorithms? That's exactly our proposal. Now, so we chose our fighter, okay? We chose an algorithm that we proposed back in 2011. It's called GPEPS. It's actually a version of an algorithm to simulate dynamics with PEPS, which is this type of two-dimensional tensor network. Now, there are many algorithms that are based on PEPS to simulate dynamics and to compute ground states and so on. They can be more or less complicated. They can be more or less efficient. I don't want to get into too many technicalities, but what I want to transmit is that this is kind of the most efficient option that we could think of. Okay, it's a 2D dynamics simulation algorithm that is actually really, really very fast and is making some approximations that in some circumstances they are completely wrong. Okay, but this is the first thing that we should try because maybe it works. Okay, there are some situations where this works when correlations are not very large. Okay, it relies on something called the simple tensor update that I can explain you more in detail if you want. Some approximations to compute expectation values. But the nice thing is that it's very flexible. It can be adapted to any lattice in any dimension, and it's actually very accurate away from quantum criticality, which is what I was saying before, that there are emerging structures in the correlations and so on. Now, it turns out that the community realized very soon that it was actually possible to simulate that with tensor networks if you chose a different type of tensor network, okay? In particular, if you chose a 2D tensor network and so on. There was a paper 10 days after the IBM paper by Miles Stoudemire and collaborators that they actually did that simulation, okay, using 2D tensor networks and belief propagation, and that was really, really very good. After that, there were a bunch of papers that were coming out, all of them simulating the system for 127 qubits. And then we went with our paper where we actually simulated the system not just for 127 qubits, but up to 1,121 and even for the thermodynamic limit, okay? So these are the processors that we simulated, okay? A is the Eagle quantum processor with 127 qubits. That's what IBM did, okay? Then we also simulated the processor with 433 qubits, okay? This is option B. They call it Osprey, and by the time that we got this paper out, that was the official IBM processor. And they were saying that that was supposed that in principle by December 2023, they will be announcing this processor here with more than 1,000 qubits. It's called Condor, 1,121. We also simulated that processor even before it was publicly available, okay? So, yeah. Yes. This is the latest processor by IBM. They announced it in February, in December. Yeah.
So this is rather rapid progress.
Yeah, they have a very,
And is the
they
noise,
are very consistent with the roadmap, yeah.
is the noise,
Yeah, you should ask that to IBM. You should ask that to IBM.
you're more up to date on
Norbert.
How do you know your results are accurate for the Condor?
Huh?
For the Eagle, I understand there are several other data, so you can compare. But how do you know that your results are accurate for
I'll show you later, yeah, convergence of the bond dimension and all that, yeah. Okay.
One simple question. So all of the matrix product state methods failed on this, right?
I don't know if all of them. I mean, I think that what they did was time evolution with an MPS. I don't know which time evolution algorithm they used. I don't know if it was time-dependent DMRZ or TBD. I'm not sure. And then they also use something that was not MPS. They call it isometric tensor networks. The time not exactly, it's not MPS, but it's also not PEPS, okay? And it was working better than MPS, but again, it was not fully working. So, yeah.
Do you see any difference when you go to bigger processors? Do you see any difference in the signal? Because we did actually the opposite. We got the system, we made a small system around the local observable they are measuring. We saw that the signal was already there, that you didn't need the extra qubits around it.
What do you mean by the signal?
So they're measuring, for example, some observable like sigma z on some qubit.
Yeah.
And that qubit has some neighbors. If you have a big enough environment, you already see the signal they see experimentally.
Agree.
You don't need to simulate the entire thing.
That's the reason why this simulation
Why this
works.
works.
I agree.
Okay.
Yes. We actually saw that. Yeah. You will see that there is almost no difference in the simulation of the system for all these processors, and even for the thermodynamic limit. We did also the simulation for infinitely many qubits in case they didn't like it. Okay, and it was exactly matching the results for 127 qubits.
The effective system is very small.
It's telling you that the correlations are very, very low. Okay, very, very low. I think they were very unlucky with this system. Okay, but I have some intuition of why this actually happened. Okay. Good. So these were the lattices that we simulated. This is the Hamiltonian. This is the operator that is the exponential of this Hamiltonian, discretized with some parameter theta h that depends on the magnetic field. And that's actually, the quantum state that we are generating. We start with all the spins or the qubits initialized at 0, and we apply this operator many, many times. Okay? And in this way, we generate the time evolution. Well, these are some examples of the results that we got for 127 qubits. That's the Eagle results. Actually, we computed average magnetizations, also expectation values of all observables over all the lattice, and we were obtaining almost perfect results with the precisions down to 10 to the minus 15, okay? Even better precisions than the ones obtained previously by Stoudemire in the first paper, but it's also a different technique, no? Things were working really very, very well, okay? Also important is the speed. We were doing the simulations on a crappy laptop with Windows with a very inefficient Python code, and it was taking us 2 seconds per point, all right, to obtain these plots. That was really very fast compared to the quantum computer that I think, according to the IBM's paper, it was around 5 hours per point, okay?
So what are the curves that are doing badly? It's hard to...
Yes, exactly. So the ones here, okay, this is MPS. Okay, exactly. This is MPS. This is the green one is isometric tensor network states. Is the one that I mentioned before. Exactly. And the ones that are doing good are the 2D tensor networks. Okay. Good. Okay, that was for 127 qubits and 5 trotter steps. It means 5 applications of this operator. Then we thought, okay, what happens if we go to larger systems? No? And it also worked. Okay, so these are simulations up to 121 qubits, even for the thermodynamic limit, very low errors, for 433 for different observables, and so on. The simulations were also extremely efficient, and we saw convergence in the bond dimension. And then we thought, okay, what happens if we go to longer time evolution? So not just applying, let's say, 5 times the operator, as IBM did. Let's see how long we can apply the operator until we start to see that the simulations stop converging in the bond dimension. Okay. Well, we did it for 127 qubits, up to 39 trotter steps, and I think it was bond dimension around 500 something. It was very well converged for 133 qubits, 38 trotter steps for 1,121 qubits, also to 37 trotter steps. As you can see, the time evolution, we still didn't see a significant divergence, in the bond dimension where the things were moving forward. I mean, when you generate a lot of entanglement in the dynamics, eventually, when you have a lot of entanglement, you should see that your results are no longer converging, okay? For different bond dimensions, one should go in one direction, another one in another direction, and it means that you are not capturing all the entanglement there, okay? It turns out that we didn't see it yet for these simulations. We are seeing now because we are able to simulate longer time evolutions, but actually, this is telling you that for much, much longer times than what IBM did, actually we were able to simulate the system with a lot of accuracy.
Sorry,
okay?
what is chi? What is chi?
Is the bond dimension of the beds.
Okay, but you're not contracting exactly.
No.
So this method has some kind of way of approximating.
Yes, there are, yes.
So I agree it converges in chi, or maybe it doesn't, but how do you know it converges to the correct value, right? Because you're using some kind of heuristic, it's like doing simple update.
It's not variational.
Just give you wrong results even when you push your button.
Agree.
So do you have a control on that? Like
no.
when it converges to the correct thing? Okay,
No, that's true. I mean, the best thing we can do is actually see that it's not diverging. Okay, not diverging. It's that it's converging in the bond dimension. Okay, but it's not variational in the sense that we are not contracting the environment to compute expectation values. Agree. Yeah. Okay. Yeah. But also.
I don't understand what your assertion is.
Huh?
So I don't understand what your assertion is for this long time.
What? Assertion. Assertion. Oh, yeah. What I'm exactly this?
You say it simulates perfectly the system.
Yes.
And then we're hearing that you don't have a certificate.
When you simulate dynamics of a system in time evolution, you generate entanglement. Okay. Now, if you generate more and more entanglement as you evolve in time, and you're always approximating with the same tensor network with a fixed bond dimension, eventually the tensor network will not be sufficient to cope with all the entanglement. Okay, and you will start to see errors. Now, if you don't know the exact result, how do you know that? Okay. Well, one way of knowing that with numerics is actually, you keep increasing the bond dimension until the maximum that you can. Okay. And the point when you plot everything, okay, you will see that everything for all these bond dimensions is kind of collapsing up to some point at which you start to see that one goes in this way. That's exactly the point where you have too much entanglement.
So you have certificate when things go wrong, but you don't have certificate when things are correct.
Exactly. Exactly.
Okay. There were some certification steps in the previous papers compared to boundary PEPs contraction.
No. I mean, say if you try to contract your whole PEPs approximately in a way where if you extrapolate all parameters, you converge to the correct extrapolation. Exactly. At least you have some. Yeah. At least in principle, I mean, maybe it might not work practically, but in principle, you can look at that extrapolation and see it converges. Whereas here it's an approximate. This method is inherently approximate, right? So exactly. At some point, you have to trust that it works or not, or get convinced from a different method. But of course, you can push it further, so it's a bit of a trade-off.
Yeah. It's also interesting to see, and in connection to what you said about the signal, that even if you increase the size of the system, all the results look very similar. It means that even for a small system, you're already very close to the thermodynamic limit. I mean, it's another indicator that, believe it or not, this is a system where the correlations are very low. Okay.
Well, the light cone is exact up to the size of light cone is like 150.
Yeah.
Yeah, but the effective light cone. So
but it's local observable. So not effective. Even exact light cone size is not larger than 200.
Yeah, sure.
Yeah, in the 20 depths, I guess. Yeah.
Nice.
So it should be exactly same up to beyond that exact light cone. It's not approximately same. It's exactly same.
Okay.
Because
comments?
it's relatively short, low depths.
Do you have an estimate of the gap here?
No, for this lattice, no. I mean, we could compute it.
What gap?
With 127, maybe it can be computed.
Yes, probably yes. Yeah.
What gap was that?
No, I mean the gap with the ground state with the first excited state. Okay.
I mean, the idea is that correlation should decay exponentially with the gap. Inverse.
If it's not critical, yeah.
If the gap is high, then your correlation are really.
Maybe I think this system has a very large gap. Yeah. And probably it's due to the lattice. That's my feeling.
Almost 1D.
Yeah. Almost 1D. Yeah.
So how far is this from the ground state?
The time evolved state. Oh, I didn't compute it.
They kicked it. What is that?
What's that word?
Specifically?
So it is a,
Yeah.
How far it's from the ground state? I don't know.
What did they take the ground state and apply some operators to it, or?
No. It's you start with all the spins polarized at 0. You don't start from the ground state.
what is the value of the magnetic field that you're using?
Of the what?
Magnetic field, H.
Yeah, actually, I don't have it here. It's right here, 1.0. Okay, this is this parameter theta h that I think is the ratio between magnetic field and the coupling. I think, yeah. But it's not the critical point, because we are in 2D. Okay, good. Well, okay, what does this all imply? Okay, the first thing that it implies is that we simulated the IPAM experiment. Okay, obviously, for longer time evolutions and also many more qubits. Now, the point is that the original experiment is fine for testing error mitigation techniques. That's very good, but you cannot claim that you cannot claim quantum advantage with respect to tensor networks because obviously it was a problem of choosing the right type of tensor networks. Okay. I think the problem here was that the Hamiltonian is too tailored to the topology of interactions. Okay, so they really matched the Hamiltonian and the lattice that they wanted to simulate to the actual topology of the quantum processor. And if you have a look at this topology, it's this heavy hexagon lattice, and it's not a square lattice. Okay, it's something else. And this lattice, for some reason, it's 2D. But remembering what we were saying this morning, that you can cut some links and approximate the contraction and so on, I think that you have to cut a very small number of links here to approximate this lattice by a tree tensor network. I think that's the feeling. So it's 2D, but it's the closest thing to 1D that you could have in a 2D system. This is my only explanation for this to work, because otherwise, I personally didn't expect this to work so well. Okay, so I was the first person surprised with this. Now, what else? Well, this question whether these lattice-based quantum computers eventually can be simulated always by tensor networks or not. This is an ongoing discussion. And whether, to me, the lattice is a very large constraint. I think that we should go to systems that are lattice-free and so on. But this is more a philosophical question. Okay. Questions before I move to the next one? You.
Yeah, you have emphasized, maybe you could just explain a little bit more, because you have emphasized a couple of times on the two-dimensional structure of your GPEPs with respect to the previous tensor networks used, that they were maybe 1D, but now you're emphasizing that this heavy hex has quasi-1D neighborhoods.
Yes.
Could you extend, maybe not now, but maybe later, a little bit on the flavors of tensor networks? So why graph PEPS is working very well, and why this ISO TNS is not working? How do we choose our fight?
That has a quick explanation. The matrix protest states are 1D. Okay. The isometric tensor network states, I'm not exactly sure how they look like, but judging from the name, the tensors are isometric. Okay, it means that they are unitaries, or the closest thing to a unitary that is a rectangular matrix, and so on. Okay, if you have a tensor network made of unitaries, it looks very nice. You can contract everything and so on, but when it comes to actually finding ground states and so on, if you have to impose the constraint of being unitary, that's a huge constraint. It's a huge constraint, and typically one needs to be careful. Okay. One needs to be careful. Now, the point is that this simple update for PEPs, actually, I think there is a paper by Frank Polman that proves that actually what is the tensor network that it's generating is sort of a two-dimensional tree tensor network. Okay, when you are cutting links and so on. So, and that's exactly that's why I was saying that this 2D system, this lattice, this heavy hexagon lattice, if you cut a small number of links, you have a tree. And I think that this is, my feeling is that the algorithm is capturing this very well. Okay. Good.
Can you give me a short introduction of the difference between GPEPs and the conventional PEPs?
Yes. What is conventional PEPs for you?
From Norbert's PEPs.
Norbert's PEPs it has nothing conventional. Yeah.
Oh yeah, maybe there is no combination.
No, in a normal PEPs algorithm, in a PEPs, you have lots of loops, okay? It's not like an MPS with open boundary conditions or like a tree. So when you want to simulate a 2D system with loops, obviously, for instance, when you want to compute expectation values, you have to sandwich the ket with the bra, and suddenly you have the contraction of a 2D tensor network, and that's exactly the thing that we were saying this morning, that is NP-hard. So common PEPs algorithms approximate this with a boundary MPS, with corner transfer matrices, with other things to approximate the contraction of the full 2D tensor network up to some accuracy. Okay, I'm not doing it here. What I'm doing here is just taking local expectation values and forgetting about the contraction of the whole lattice. Okay, the same story applies not just for computing expectation values, but also for computing the update of the tensors as the time evolution goes through. Okay, so every time I apply a gate, I have to update the tensors, and to update these tensors, to do it well, I should actually do it variationally in such a way that I minimize the distance between the truncated tensor network and the original one, and this involves again a contraction of all the tensor network and so on and so forth. I'm not doing anything like that. I'm just doing an update that is entirely local, forgetting about the rest of the system.
Okay. What is the biggest difference between the belief propagation algorithms?
Between?
The CCQ people did, yeah.
Oh, the belief propagation.
Yeah, because it also shares similar spirit.
Yes, but the contraction, the story about the contraction, you find it all the time. No? Yeah. Okay. I think there was another question. Yeah.
I have a question and a comment. So, regarding to what they said a minute ago, so is there a big difference between the methods? Like ISO TNS, for example, they are actually contracting. I know it has all these constraints, so the contraction is easy.
Yeah.
But you can only handle so much bond dimension, but here in these approximate contractions, which are not actual contractions, you can afford very large bond dimensions.
Yeah, no, but I'm not explicitly contracting the lattice at any time.
Right, so you can afford much larger bond
Yes.
dimensions. I wonder if that freedom
I can go to
like
bond dimension 500 in 2D, but because I never contract the lattice.
Right.
Okay.
Is that a key point in why you can?
Yes. Well, it's a key point to be able to reach bond dimension 500 because
Sure, but in convergence,
otherwise it will be too expensive to contract the lattice. But it turns out that if I approximate this contraction by local weights, it works super well.
Yeah.
Okay.
The comment is that since these experiments have effectively a very small volume, you're already in the small chip, you have converged to the thermodynamic limit pretty much. That gives also the experiment a lot of robustness in the sense that it doesn't see errors happening too far away from the observable, so it's not really probing a large system.
Agree.
They measure a strong signal because of the same reason why it's easy classically.
Probably yes.
It works very well.
Yeah, that's a good point.
So they go hand in hand.
That's a good point. Okay. Yeah.
Could you roughly explain how to calculate expectations without the need of contracting the lattice?
Yes, it's an approximation. Oops, it's actually an approximation. It works in the following way. So let me do it for 1D. Okay. Now imagine that I have an MPS that looks like this. Okay. And now I want to compute this expectation value. I have an operator here. Okay, so this is the ket, this is the bra, this is my operator. Here I have to contract all the lattice. Okay, the same story for 2D, but with a 2D system. Okay, now what happens if you have something else? Okay, imagine that here I'm going to introduce some extra matrices. Okay, here, that the people in quantum many-body physics know as the Smith coefficients. Okay. And these actually correspond to some weights. Okay, when you compute the MPS in what we call the canonical form, okay, there is the composition of the MPS that looks like this. Okay, you could do something.
So, are all the circles representing physical vector spaces, or?
Yes, physical vector spaces are these lines. Okay. Okay.
So that in between one, it's not really.
This is an operator. Okay. This is what we. So this will be psi o psi, or if you want, this will be.
Okay. And
Psi daga times o times.
what about those little ones you just stuck in a moment ago?
These ones.
Yeah.
Okay, these are extra tensors. Okay, these are matrices that correspond to singular values. Okay, these actually. So if I have, let's see, imagine that I have this tensor. Okay. Now I just do this splitting between left and right, and I do a singular value decomposition here, and I decompose it like this. Okay. This is the matrix of singular values. That's exactly what I'm doing there. Okay. Now the same story. Well, actually, this will be to compute the expectation value. If this is in canonical form in 1D, we know that this is exactly this is a mathematical calculation, but one can see that everything to the left and to the right is canceling, and at the end of the day, this expectation value is going to look like, let me see if I get this correct, like this contraction, okay? Okay, so I only have the tensor corresponding to this side, and this is because all these contractions correspond to the identity operator that is right here, okay? This is exact in 1D with open boundary conditions. So what I'm doing is in 2D, I'm assuming that this is also true, which is not, okay? So I'm doing something like this also in 2D. It's a very brute force approximation, and shouldn't work, but if the correlations are very low,
Where do you get a similar value matrices from in 2D?
Huh?
Sorry.
He first.
Yeah, it almost seems like you need some type of a tree structure for this to be
Exactly. That's what I'm saying.
That kind of looks like
it's a tree approximation.
In that regard.
It's a tree approximation in 2D. Yeah.
So where do you get the singular value matrices from? I mean, 1D I see where you get them from, right?
In 2D?
From somewhere, but in 2D you have to get them somehow, right?
We get them dynamically, okay, from the simple update.
Ah, okay. So you start with something in the
I start with a quantum state that is everybody 0, and then just apply a gate and do
the
singular
initial state
value.
it's fine,
Turn
and
off
then
all
that's
the
a
computer
Exactly.
values.
I just get the singular values and keep them. So I get something like
in
this.
that case, if you do simple update, there is a canonical way of getting this decomposition, so to say. It might not be correct, but
Yeah, into the,
at least locally you get it.
yes.
So even 1D is not exact then.
With open boundary conditions, yes.
I mean, if you update that way, because is it exact?
If you do simple update.
If I do simple update in 1D, it is exact.
Because it's unitary. Because it's unitary.
Exactly.
Yeah. Imaginary time is just not exact.
Yeah. And it's also exact for a 3-tensor network.
Yeah. The real-time TBD is exact.
Okay. More questions or comments or provocations? No. Okay. So, well, then let's move. Let's move to the next topic, which is machine learning. Okay, this is, now we are changing gears, okay? This is a completely different story. It's not about the simulation of a quantum computer. It's about picking up ChatGPT and making it cheaper, okay? Turns out that we also did it using tensor networks, and it has to do with this story that is called large language models. So here I'm going to explain everything at a very high level, okay? I will not enter into very technical details of machine learning because maybe those are too heavy, but if you are interested, I'm going to be here all the week, so we can talk anytime, okay? Now, what is generative AI? Okay, I'm pretty sure everybody has heard about this. So this is a type of artificial intelligence, okay, that is capable of generating text, images, media, music, patents, papers, whatever you want, another type of data, and it's based on learning the structure of the structure and the patterns of input training data, and then replicating it in new situations. Now, this is very interesting. The impact is huge. It goes from improving the current procedures that we have to destroying whole humanity, okay? And there is a lot of debate about this. Now, examples, ChatGPT, okay? This is pretty awesome. You can just throw a prompt there, and it looks like it's able to generate almost anything you want, okay? ChatGPT is not the only language model that we have. Meta, which is the matrix, is actually the company that is behind Facebook. They're also very strong working on this. They have their own models. They are called Llama. Okay, these are also considered large language models on the same footing as ChatGPT. And the nice thing about Llama is that they are open source. Okay, I mean, the story says that there was somebody working at Meta that just decided to put that on open source, and then they could not do anything and decided to open the code for everybody. And there are all these repositories in something called Hugging Face and so on that you can find all these models. Okay. You can also generate images. This is this algorithm by OpenAI, DALE, and I think that this is also integrated in ChatGPT-4. You can tell ChatGPT to draw an image of whatever you want, and it actually does it for you. Okay. All this is super impressive, but there is a big problem. Okay, which is that the energy consumption is huge. These algorithms are the most inefficient thing that we have ever seen, okay? Training, and this is something that, this is an assertion by the CEO of OpenAI, okay, by Sam Altman. He recognized that training ChatGPT-4, it was $100 million in electricity bill, okay? So they almost need a nuclear power plant next to it to actually make it work, okay? And the last declaration that he made was that, these new AI systems, we are in, how did we say it? I think he said, we are in urgent need of new energy sources, okay? So, instead of thinking about making the algorithms more efficient, the guy just wanted to make nuclear fusion or something to feed the AI, okay? So, well, that's a legit point of view, okay? But you can see also how is the energy demand over the years. This is a plot from The Economist of the energy consumption of AI systems over the years, and
I think this looks worse than it is because
it's double exponential.
It says floating point operations.
Yeah.
So the energy per floating point operation has hopefully gone down since.
And notice that this is on an exponential scale, and this is growing also exponentially. So it's growing as twice an exponential. Okay, ChatGPT-4 is up here, but you can see that this is growing at a rhythm that is entirely insane. Okay.
Yeah, but still, it's not the energy. No, I think it's important.
Well, but it's proportional. It's easy to make the translation. Okay.
Probably the energy per floating point operation went down exponentially.
Maybe it's even worse.
No, I think it's better. It's better. No. I think it's slightly unfair.
Okay. Well, but it wouldn't.
From The Economist.
That point of view. Okay. In any case, either when I see this plot, the first thing I think is about finding a more. I mean, we are obviously doing something very wrong here. We are training ChatGPT-4, okay, consuming so much energy, and it still doesn't work well, okay. When you see any system in nature, you see any animal walking and so on. That's a biological intelligent system that is not consuming the energy of a nuclear power plant. Okay, so it obviously means that we have something wrong, definitely very wrong in the algorithm or in the hardware or something. No. So we need to do something. Okay, this is a problem with AI. It's very cool, but it's consuming too many resources, and on top of that, the demand is also exponential because now everybody wants to use this, no? And we have really a problem with this. Now our solution, well, use tensor networks. Okay. How can you do that? Well, actually, there are some parts in machine learning algorithms where you can use tensor networks to make them much more efficient than what the people are traditionally doing. Okay. For the specific case of large language models, there are this type of machine learning architecture that are called transformers. They were proposed by Google, actually. And I will not go into the details of this, but the point is that there are some places in this architecture where we find deep neural networks. Okay, deep neural networks, you have layers of neurons, layers of connections, more layers of neurons, and so on. And it turns out that it's possible to make neural networks and deep learning much more efficient in memory, okay, by decomposing something that is called the weight matrix in terms of tensor networks. For instance, a matrix product operator. At some point, we have operations like this: matrix times vector plus a vector of bias equals to something, and then we apply what is called an activation function, or sigma. Now, it turns out that this weight matrix is huge. This is what is consuming most of the memory in a deep learning structure, and we can decompose it by using a tensor network. A matrix product operator is an example, but there are other options, okay? Now, in these transformer architectures, we can apply this trick in many places, and then you can compress a lot the memory that is being used by a language model, okay? We actually put forward this paper in January, where we actually did this for a large language model. Now, I'll show you the benchmark that we did. We pick up a model from Meta, okay, from the ones that I was explaining before that were kind of competitors of ChatGPT. This is a model that is called Llama 2 7B. Llama 2 is the latest generation of language models from Meta. 7B means that it has 7 billion parameters. So this is already large, okay? Actually, this family has 3 types of language models with 7 billion parameters, 13 and 70. These are huge. And the smallest of the large language models is the one with 7 billion parameters. That's the one that we did, okay? It has other structure here, it's processed, it's been pre-trained over 2 trillion tokens. It means essentially over the entire internet, a context length, and so on, and so fine-tuning, and so on and so forth. Now, roughly speaking, what we did was to pick up the structure of Llama, which is open source, okay? And at those points where we saw that we could apply a tensor network, we just applied it, okay? There are some places, if you go into the details, for instance, that are called self-attention layer and multi-layer perceptron layers and so on. These are the places where we see that there is a deep learning structure there, okay? And there we went and substitute their functions by our functions, as simple as that, okay? Well, and by doing it, guess what? So we pick up Llama 2 with 7 billion parameters, matrix product operators with bond dimension around 200. We also reduce the precision of the numbers from 32 bits to 16 bits, which also improves the memory consumption and doesn't reduce too much the accuracy. And we were able to reduce by 85% the memory, okay? We went from 24 gigabytes to 3.7 gigabytes. So, from the huge model that we had at the beginning, we ended up with something that was 15% of the original one, okay?
Is there some one-dimensional geometry?
No, there is not. We use that's
just efficiencies of MPO.
We chose this fighter, yeah, because it's very efficient. It's efficiency of the MPO, yeah. But another thing will be to try other types of geometric structures here or tensor networks, for sure, yeah. But no, it's not at all one-dimensional, not at all, yeah.
Is it trivial to find MPO representation of those blocks?
Well, you can do exactly this sequential singular value decompositions.
Iterative SVDs.
That's a way of doing it, and then a little bit of an extra update to improve the accuracy or retraining. Okay, that we did. Yeah.
Is the tensor network representation useful in practice for training, or?
Yes. Yes. But you
Reasonable
have to redefine the training algorithms for the tensor network. Yeah, I mean, it's not the same training algorithms that you had for the original structure.
with the saving in energy or time to
Yeah.
proportional to the saving in memory?
I'm just going to show you.
Okay.
Yeah.
So just to confirm, this is post-training, right?
This is?
This is post-training.
This is post-training, exactly. This is, we compress a pre-trained model.
Now, in terms of the total number of floating point operations, have you gone down, or is it just the memory footprint that has decreased?
It has gone down. Yeah, I mean, we can reduce the memory, but then the retraining of the compressed structure is also more efficient.
No, but what I mean is that once you, I mean, ultimately, when I use it, I care about how many, I mean, even generating something with this is a non-trivial computation, right? I mean, even using it is a non-trivial computation. So does that improve in terms of the number of floating point operations versus just the memory footprint?
Yes. It also improves in terms of the number of operations, yeah. The overall algorithm is also faster. Yeah, and not even that, also because retraining these models these models are so large that you cannot train them in one single machine, so you have to do distributed training, and there the bottleneck is the communication between GPUs, and we also reduce that communication. Yeah. Okay, more questions? Yeah.
Let me just understand. Here, the basic thing that you're doing is compressing the matrix W, or is
in this specific case, yes.
Oh,
yeah. There are more things that one can do on top of this, but at this level, just that. Okay. Well, as I was saying, 85% of memory reduction. Now, if we have a look at retraining times, okay, it's also twice faster for the compressed model. We actually did retraining for some data sets that are open source called GigaWord and XSum, okay? And when you have a look at the accuracy, again, for these two data sets of the retrained models, we keep more than 90% of the accuracy of the original model, okay? So long story short, we reduced the model to 15%, okay? The training and the speed of inference and so on is twice as fast. And then we keep the accuracy more than 90% of the original one. So the loss of accuracy is kind of acceptable for the huge truncation that we actually did. Okay? Yes?
I remember when ChatGPT came out, they made a lot of emphasis in the fact that they had been training. The bulk of the training was a simple part, and then they had a bunch of people actually that they hired to train real humans and tuning it, and that was where the advantage came from. So I wonder if if losing 5% of accuracy means for a human interacting with a human that it really gets worse, or not really.
Depends on your tolerance to error. Okay, losing like 9% of accuracy. I mean, for the checks that we did, it was actually the output was completely acceptable. Yeah. But it could still be retrained the structure. So eventually, now the problem is that even if it's twice faster, it's still computationally expensive. But
so I wonder in the original models in Llama 2, when you go from the 70 billion parameter one to the 7 billion parameter, which is a 10th.
Yeah.
Obviously. So how much accuracy do you lose in that?
That I don't know. I should check. That's in the website of Llama.
I see.
Yeah, that's in the website. Yeah.
Thanks.
Yeah.
This is kind of a general question, but do you know how you score the accuracy? Like, what do the tests?
Yeah, it depends. For these language models, they have everybody has a different score for the accuracy. Okay, there are different metrics like BLEU, ROC, I don't know. This one in particular, the one that we check is one called Roach, which means it's actually a family of metrics. Okay, this one, for instance, is measuring the overlap between unigrams. Unigrams are words. Okay, the second one is between bigrams. Then Roach L, I think it's the longest common sentence in a text, I think, or something like this, and the same story for the last one. So there is actually different families of scores. Yeah. There was another. Yeah.
When you do the retraining, do you fix the rank that you have
Yes.
compressed?
Yes.
So
So
is it possible to, if you do rounding or truncation, would it be difficult to do the backpropagation or the adjoint solves then?
No, it's actually, so what we do is we have a pre-trained model. There are different things that you can do here, okay? What we do is we have this huge model that is already trained, and then we truncate it, okay? Now, this truncation is quite local, okay? It's just this, these sequential singular value decompositions, let's say, or something like this. And then what we do is we retrain it to ramp up the accuracy, all right? Now, this retraining, okay, it takes a little bit of time, but it's actually not so much, and it can be done, okay? Another thing that you could do is to start directly from the structure already, like an ansatz, okay, completely empty, and train it from scratch. Okay, that we didn't do, but it's also be possible.
I'm just thinking that when you have truncation, if you have an adaptive step, they're computing the gradients of the loss function may be a little bit complicated.
You have to redefine your libraries yes, for these structures. Yeah. Okay. More questions?
And the ordering of the modes here is just arbitrary, or?
Yes, there is no, I mean, yeah, I agree, it's arbitrary. There is no, as I was telling Steve, there is no one-dimensional structure here at all, not at all.
Yeah.
So it's an ansatz, okay? Yeah.
Is there a way in which this would scale up in a favorable way? Because, you know, if you want to slow down the exponential growth of energy consumption, then a factor of 2 doesn't really make a difference.
For speed, but for memory, we reduce 85%.
Yeah, but that's probably not the energy-intensive part.
Yeah, well, I mean, the nice thing about this is that you can concatenate it with other compression techniques. Okay, so the people in ML, they actually, I mean, this is as an option, but they are trying other things. They have something called distillation, where they just remove layers from the neural networks, just brute force, or pruning, where they just remove neurons. Okay, it's like a very brute force thing. And with this, they can actually even compress it more, or low rank approximations, and so on. So you can do all that on top of this. Yeah. Okay, more questions? All right, well, so what does this imply? As I was telling you, we just compress Llama 2 with 7 billion parameters down to 15% size, keeping more than 90% of accuracy. That's a big compression with tensor networks, okay? You save a lot of energy, also faster times. And as I was telling Norbert, this is compatible with other compression techniques in machine learning, okay?
In which sense compatible, by the way?
Oh, well, it means...
This is a bit of a low-rank technique, and, you know, doing a low-rank decomposition is a low-rank technique. So is it clear that you could combine them?
They are different low ranks.
Would add up?
They are different ranks. What the people mean by low rank in machine learning is a different low rank.
Did you try, or if not, it would be nice
no, not with low rank.
This combined with something else and see that you actually...
We tried with something called quantization, which has nothing to do with quantum, okay? Exactly. So it's reducing going from, from integers, from numbers with 32 bits to 16 bits or something like this, reducing the precision of your floating point operations, okay? That looks like a kind of a trivial thing to do, but turns out to reduce a lot of the memory, yeah? Okay, and in combination with that, it works. And now we are also testing with the rest. Okay. Well, and apart from that, the nice thing that I like about this is that if you compress a lot of the memory, you can deploy LLMs on premises. As I was telling somebody this morning. Yesterday, I was flying to LA, and the internet connection in the Lufthansa plane was super bad. Okay, so I couldn't connect to the cloud to actually finish the presentation or do whatever I had to do. And then I thought, you see, I mean, if everything were super efficient, I could deploy it on premises, and I wouldn't have to connect to the cloud at all. Okay, so that's. Believe it or not, this is a very important application. Imagine that you want to deploy AI on a satellite, okay, or something like that. So that's important. And obviously, we can deploy more complex structures and training algorithms and so on. Well, okay, that's everything that I wanted to explain you. I think we are more or less on time. Apart from that, thanks a lot for your attention. And we are hiring, okay? We have several open positions to people interested in tensor networks to work on machine learning, on optimization, on simulation of quantum computers and other very interesting stuff. So if you're interested or looking for job opportunities, let me know. Thank you.